All right, so into the week here, we're talking about calorimetry, and so this, to be clear, this is an experimental technique, and so this is something that if we were doing labs in person right now, you would definitely be doing. Instead, you'll be simulating it at some point. Maybe you already have. I have to see what labs you're doing. I'm in lecture mode right now. When you don't walk into a room and do the lab twice a week, it's a little easier to let it slip your attention. Like 6 hours, or well, I think it's like 4 here, hours a week doing something. Yeah, I'm very aware of what's going on. When I'm just like kind of like checking in every now and again, I kind of have to check in and remember what's happening, to be honest. So this is experimental technique. It's a really fundamental type of experiment. So how do we know what the heat capacity is for a substance? We just have these values on the table. We can look them up. That's great. But like, how did they get on the table? The energy change for those phase changes, delta H fusion, delta H vaporization. How do we know what those are, right? So again, for us solving problems, we look it up on a table, but how did it get on the table? And then energy changes for reaction, delta H reaction. How do we know what that is? And so there's kind of two options here. One, you do some really complicated calculations, well beyond the scope of this class. So guess what? This option's out. And if you're really good, you're within 5%. And I'm serious. 5%, you're good. If you get it down to like 1%, like you need a better hobby. You get those values. You calculate them from like raw, quantum mechanical data, statistical mechanics, that type of stuff. Or using nothing more than essentially like a thermos or a styrofoam cup, a thermometer, and the reactants, you can measure. And so calorimetry is the experimental technique of measuring things that let us figure out what delta H is, what specific heats are, what delta H reaction or phase change, whatever it is that's going on, we measure it. So there's some key stuff here. And I've been trying to lay the groundwork on a couple of these ideas. I'm talking about like surroundings and system a little bit, mostly surroundings. But now we're going to really play off of that. So, energy is conserved. I know I've told you this before, I'm going to tell you again, because it is absolutely paramount, fundamental to this experiment. That energy is not created or destroyed, but kind of shuffled around, right? So it's any energy gained or lost from like a reaction, say, well, where does that energy go? Or where does it come from? If it gains energy, where did it take the energy from? If it loses the energy, where did it go? It doesn't just disappear into nothing or appear out of nowhere. It gets dumped into the surroundings or taken from the surroundings. So it is exchanged with the surroundings. And so what we have is what we call kind of a system surroundings kind of framework. I hid the surroundings from you. Okay, and so what we have is that we've got the surroundings surrounding our system, right? Energy / heat is exchanged. If the system needs to dump energy off, it just dumps it in the surroundings. If it needs to pick up energy and absorb it, it absorbs it from the surroundings. And so generally our system is what we care about. Like, it's the reaction. The surroundings, well, that's the whole universe. Okay? And so what underpins all of this conservation of energy, is the first law of thermodynamics. There's 3 and a 0th law, and if you want to hear about the rest, that's a couple chapters away. That's actually next semester. But you do get the first law today. You don't have to wait for the first law. Come on down. Whoops. law of thermodynamics. And what it is, again, is just that energy is conserved. But we just dress it up fancy mathematically. Alright? And we just say, okay, well, the change in energy of the universe is 0. The total amount of energy is constant. We just put it in different places. We just move it around. Okay? My house is hot. I want it to be cooler. I move heat energy outside my house. I take it and I move it into the surroundings. I put it in some other part of the universe that's not my house. Or, conversely, if it's cold, I try to hoard some energy into my house, keep it warm. So, what does that mean in terms of system and surroundings? Well, if there's a change in energy for our system, then there's an equal and opposite change in energy for the surroundings, so they cancel each other out and add to 0. So if my system absorbs 10 kilojoules of energy, the surroundings lost 10 kilojoules of energy. So this would be a plus 10, a minus 10. We add them together, we get 0. That's conservation, right? All the pieces are accounted for. They're just somewhere else. Okay? So, calorimetry is a technique where we kind of carve out most of the universe and make it not matter. We try to separate our system and its immediate surroundings from everything else. So we don't need to worry about, the moons of Jupiter or, the tides in the Pacific Ocean or any of that stuff. We don't even need to worry about necessarily what temperature the room is, because we're going to isolate a very specific piece of the surroundings. And to do that, we use insulation. We use styrofoam, insulated thermos, whatever it might be. There's the more insulated, the better. So what we have is, first off, we're going to be measuring change in temperature. So we need a thermometer. Right? Maybe use a digital thermometer. That's cool. Definitely more efficient time-wise. And then what we do is we put this thermometer in an insulated box. Seeing the height of my art skills right here. Look at that. That hashing and that shading. It's incredible. How you know it's insulation? Postmodern aeropointillism. Insulated container. There you go. How you know this is a thermometer? Because I'm going to put a big old arrow pointing at it, and then I'm going to write the word thermometer. That's how you know. That's how you know who you're dealing with, okay? Now inside of this box, we're going to have water. And what we're going to do is we're going to perform the reaction in the water. So we have a known mass. We know exactly how much mass of water that we have, plus everything else we put in there. Okay? So, the reaction happens, and if the water gets colder, that means the reaction is endothermic because it absorbed heat from the water. If the water gets hotter, or temperature goes up, then it was an exothermic process and it released heat to the water. So what we have are surroundings. We have immediate surroundings, but they are cut off. So it doesn't matter what's going on out here. It only matters what's happening here. So the reaction is the system. And then the solution in the calorimeter. This is a calorimeter, this whole thing. Is our surroundings. It doesn't exchange heat with anything else. Now in reality, you can have better or worse insulators, so it's a better or worse calorimeter. Alright. Now why do we do this? Like, why don't Why don't we just measure the reaction directly? Well, how do you put a thermometer in a reaction? How do you just like poke? What's your do reactions have temperatures? No, they don't. Their surroundings have temperatures. So we have to monitor the surroundings and infer what the reaction did from that. And so what we're doing is creating a situation where 0 is equal to the sum of our change in heat of reaction plus the change in heat of surroundings. So if the surroundings gains heat, the reaction lost heat. If the surroundings lose heat, it was taken by the reaction. Okay? So, in addition, what can we say about our surroundings? Well, we just go MC delta T. We know the mass. We'll measure the change in temperature. And we'll know a constant for this. Usually we just use the one for water. It's a dilute solution. And so that's what we do. So that's kind of like the experimental setup. Like this is the whole thing. And so when you do this lab in person, no joke, every school I've worked at, maybe this one's different, maybe they got something fancier, but every school I've worked at, we just give you a styrofoam coffee cup. Some schools have lid technology, some don't. Looking at you, University of Oregon. And that helps prevent error because you're not losing heat to the surroundings through the top. So if you can put a lid on it, that's great. And you can get decent results. Now there's some really high-end calorimeters that are really nicely insulated, screw on very tight, no air exchange at all with the environment. Very, very effective. And those work well too. But, why would we spend all the money on that when we give you a 25-cent styrofoam coffee cup and just be like, have at it? Oh, by the way, when you're stirring, be careful not to punch a hole in the bottom. Yeah, guess what we're going to do? We're going to give you the 25-cent cup and have you make hay. So, when you do calorimetry, you're going to have a recorded mass of everything inside the calorimeter. You're going to have a change in temperature, and then you're going to solve for the Q of the reaction. And then we'll talk about how you go from that to delta H reaction. Okay, so there's an extra step in there. So, let's do a practice problem here. Let's do an example. So we've got a calorimeter. That should tell you you're doing calorimetry, right? That's a pretty good clue right there. So it's going to have 100 grams of solution. And we record the following temperature. So it has an increase from, you read it before the reaction. You can see 22.0 degrees Celsius, and it increases to 35.0 degrees Celsius. So that's convenient, 0, so I don't have to do any math on the tenths place. That's nice. And this occurs from a reaction. Or it's from a reaction that occurs inside of it being the calorimeter. Question 1. What is the heat of the reaction? What is Q reaction? What's heat of reaction? Alright, this is a two-step problem. Step 1. Find Q of the surroundings. What's going on in the calorimeter? Well, it's MC delta T. This is a water-based solution, so it's going to be 4.184 joules per gram degree Celsius. The gas law still has me trying to save mole Kelvin, so I got to watch out. Hopefully that's not happening to you guys. Alright, so what's my mass? Well, it's 100 grams. How do I know it's 100 grams? Because I have it off screen. That's why you know it's 100 grams, as you can see right there. Alright, what's C? Right there. 4.184. Then you can also see that it's going to be joules per gram degrees Celsius, so my grams are going to cancel. That's nice. Now it's just joules degrees Celsius. What's my delta T? I went from 22 to 35, so that means it went up 13 degrees, 13.0 degrees Celsius. That's also going to cancel, so I'm just left with joules. Well, that's pretty nice. I punch up the math, I get 5,440 joules. That's a pretty good chunk of heat, right? And so that's a comma, just to be clear. 5,440 joules. 2. We're not done. We gotta find Q reaction. But we're basically almost there. Q reaction is going to equal -1 times Q of the surroundings, because they're equal and opposite. And so it is -5,440 joules. Isn't the conservation of energy beautiful? I just take that, put a minus sign in front. If it was negative, make it positive, so on. So just flip it. I just flip it. Now this is what I was warning you about earlier when I said the positive and negative signs, addition and subtraction, that type of thing. They're borderline weaponized in this chapter. And so a lot of times you're going to do the numbers and just be like, oh god, is it plus or minus, plus or minus, plus or minus? Flip a coin, whatever, or just remember you just flip the sign one time. Because again, we can't measure the reaction, we can only measure the surroundings. Whatever the surroundings did, the reaction did the opposite. So we flip the sign. And guess what? By the way, we're done with that question. That's Q reaction. Bing. That's it. But let's add another wrinkle to this, okay? So if this reaction involved 0.15 moles of limiting reactant. You notice I'm being so vague about this reaction. It's almost like I don't know what it is. Alright, well, what is delta H reaction? So now we actually have all the pieces to find delta H reaction. So here's what you need to remember. Delta H reaction, well, it's going to be something along the lines of kilojoules per mole. I see moles, guess what I'm going to do? I'm going to divide. So it's Q, reaction over moles, okay? And then I just got to make sure it's in kilojoules. So delta H reaction equals -5,440 joules times 1 kilojoule per 1,000 joules divided by I only got 1 mole value, so why not use it, right? And it could be limiting reactant, it could be product formed, but generally you're only going to see one set of moles. You see moles, you see that you got to find delta H. You've already got your Q, your Q reaction. You just set this up. It's Q reaction kilojoules divided by moles. You're home free. That's the whole process. Because we're scaling this per mole of whatever it might be, limiting reactant, product, whatever it's given. And it comes out to be -32.3 kilojoules per mole. What a beautiful delta H. Is this an endothermic or exothermic process, by the way? It's exothermic. It lost heat energy. It heated up the surroundings. Heat exited our reaction. And so sometimes you'll see things like, well, okay, well, what about the surroundings? What happens with the surroundings? I don't like to play those games, I'll be honest. Because it's kind of like the reaction is the, it's the train engine. And the surroundings are kind of the cars. Okay, they're the cars stacked on the engine. The engine decides if you're going forward or backwards. The cars are just along for the ride. So it makes sense that the active participant, the reaction, is exothermic or endothermic. The surroundings are just responding to that. And so my advice is, whenever you're dealing with that stuff, if you ever see it on an ACS exam or whatever, track the system. Unless you're doing calorimetry, because you got to track the surroundings and flip the sign. But in general, I always hang on to what is the system doing, and then if there's ever a question about the surroundings, you know what I do? This is beautiful. I just flip the sign. I just flip from endothermic to exothermic, or exothermic to endothermic, whatever I gotta do. And so it's like, oh, my reaction is exothermic. What are the surroundings doing? They're being endothermic. This is dumping heat. Heat's exiting here. Well, where's it exiting to? Oh, it's exiting to the surroundings. So the surroundings are, heat is going into the surroundings, endothermic. But I don't like to spin my wheels on that too much. Again, just worry about the system, and then just do the opposite. Okay? No need to get lost in the weeds. Just pay attention to the system, and then worry about the rest. Now, this is an example of a heat exchange calorimeter, or a coffee cup calorimeter. There's a few different names. There are other types. So you can't always do a reaction in water. For example, you're going to have a hard time performing a combustion reaction in water. Alright, so this isn't always going to work well. So there are actually other types of calorimeters. The next most common type would probably be what's called a bomb calorimeter. Don't ever try to bring one of those on an airplane. Professional advice. And so it has a different design, and so that's something you can use for like combustion reactions. And then there's a few other twists on these as well, but those are like the main two. I'm not going to get into them too much. There's a homework problem or two with them, and my advice is just follow the units, do unit analysis, and you'll get through fine. That's all you got to do. They're actually easier than this problems. You can find that, if you can believe that. Alright, so that'll do it for this week. We're going to pick up the chapter, finish it next week. If you want to get ahead a little bit, we're going to pick up with Hess's law. We're going to go through enthalpies of formations, or I'm sorry, standard enthalpies of formations. We're going to talk about the stuff at the very end, the energy associated with chemical bonds. So those three topics are actually really nicely tied together. So I'm really happy I could set them aside for their own week. They are going to build on the idea of enthalpy that we talked about this week. And any value that's associated with them is actually probably measured through calorimetry. Keep that in mind as well. So, if you don't have time to get started on it, that's cool. That's fine. We'll talk about it next week. So there is no chapter quiz this week. That'll be next week when we finish the chapter. But there is homework. So don't dilly-dally on that, because you really want to nail these skills down, because we are going to expand on them dramatically next week. Alright, and as always, if you have any questions or you need help, don't hesitate to contact me. I've got office hours. I respond to the Canvas messages. I will be revamping the help forums, so they're a little more streamlined. And I think I finally fixed my settings, so I'll actually know when someone posted a help forum. So that's great. And again, I've missed a couple, and I apologize. I thought I had the setting where it would message me so I would know, but apparently I didn't. I think I have it now. But if you don't hear from me after like a day, feel free to send me a message on Canvas, and I'm happy to help. It's just apparently I'm not as good at technology as I used to be, which means I need to take the high road, and I blame technology. That's right. It's not my fault. I blame technology. Alright, so this is often a difficult subject for students. Thermochemistry is not often simple, but watch your units and be very careful about plus or minus, and you'll get through it all right. But if you're stuck, like I said, let me know, and have a good week.